Hello, good day. My name is Arief Budiman. I'm a faculty member in the Industrial Engineering Department, BINUS Graduate Program, Master of Industrial Engineering, BINUS University in Jakarta. Today, I'll be talking about modeling crystallographic anisotropy dependence of interfacial sliding phenomenon in nanoindentation of copper niobium ARB, that is accumulated rolling bonding nanolayers. Here's the outline of my talk. First, I will be talking about the unique characteristic of copper niobium ARB sample, and then how we perform and why we perform nanoindentation experiment on this unique sample. And then thirdly, we reported our simulation result using finite element modeling, and then we conclude. So what's so unique about this copper niobium accumulated rolling bonding sample? So the ARB process has been reported first, I think, about 5 years ago, and since it has since been receiving wide attention from many researchers in the world. The ARB sample is obtained by a rolling process such as shown in here. We started out with millimeter layer thickness of copper and niobium and copper, but we keep rolling it, and every time we're rolling it, we are bonding it, and then we keep bonding it until we end up with many layers of copper and niobium, each individual thickness of about 16 nanometer. Uh, and then it turns out that because of the way it is being produced, especially in the rolling direction, the interface develop a very unique characteristic. So we see here the zigzagging morphology. That is because of the sheer amount of deformation that is happening in the rolling direction, as you can imagine. Uh, Such a zigzagging morphology. By the way, the ARB process, the sample, and then as well as this result of the zigzagging morphology have been reported in these papers that we cited here. So it's not our current result. This is what we have seen in the literature. So this zigzagging morphology makes it that it is very less likely to for the interfaces to slide against each other. In other words, they are almost impossible to shear on the interfaces. Uh, so they are basically interlock interface. Whereas in the transverse direction, what happens is very different because of the transverse is basically the into the plane, right? The direction of the into the plane orthogonal towards this rolling direction. So the interface characteristic there is pretty flat, pretty plain, and because of that, it has more sliding potential. So upon deformation, the nanolayers is more likely to slide or to shear against each other on the interfaces. Okay, and that forms our hypothesis. Our hypothesis is that if we have a deformation that is along RD and then along TD, we should see very different properties or very different uh, output or result. So we plan to do nanoindentation with a Berkovich indenter such that one of the main axis, there are three axes in the Berkovich indenter, but one of them is aligned to the RD direction of the sample, and the other is aligned to the TD direction of the sample. Thus, the main or the deformation is dominated on the direction of the RD here, and here the deformation is mainly on the TD direction. So our hypothesis is that in the TD, because the interface is more likely to slide against each other, then there is less deformation of co-deformation of the layers. In other words, the deformation is mostly happening with the layers sliding against each other. And also that's because higher yield strength of the individual nanolayers of copper and niobium that is reported also in the reference number 1 here. So this less interfacial sliding or this more interfacial sliding in TDs also has been reported by reference number 2. So these two references are the basis of our hypothesis, and it will be cited over and over and over actually in the next few slides. So in the RD, in the opposite, we see that the interface is interlocked. So it's basically there is no interfacial sliding, and also based on reference 1, it has lower yield strength and thus higher plasticity. And because of that, we think that in the RD, the deformation should be much more disordered. And because of that, the palp, which is basically what happens in the Berkovich nanoindentation right here, this is the area of the palp, it should be higher in RD than in TD. And true enough, we do a surface profiling of the indented surface using SPM, and this is the result. And from here, we can calculate what is the surface palp, which is basically this area. And indeed, we observe that the surface palp due to the Berkovich nanoindentation is higher in RD, which is the black data point here, compared to in the TD, which is the blue data point here. So indeed, experimentally, it is observed what we hypothesize. So next, we attempt to simulate the nanoindentation experiment, partly also to explain why it is so. So obviously, by having the modeling, we can quantify some of the properties difference between the two direction, RD and TD. So both in the individual nanolayers based on the crystallographic orientation, as well as because of the morphology or the morphology of the layers during the formation. So we see different RD and TD properties of the nanolayers. But the biggest difference is really in the interface characteristic. The interface in the TD is modeled to be with much lower interface shear strength. That means interface sliding is likely to happen, whereas in the RD, it's modeled with very high interface shear strength. That means it's less likely to happen. Interface sliding is less likely to happen. So the load displacement curve, the solid line is the experimental, the dotted blue line is our model. So we see that we can approximately replicate what happens experimentally, so that increases confidence about that our model is indeed simulating what happens in the real experiment. So true enough, you see here in the RD, we see as the indenter comes into the material, it starts deforming. And then you see some of the this is the stress mapping, the stress distribution, but you start seeing some of the co-deformation and some of the much more disordered deformation. And this is what happens right here in the palp area. You see that it's and this is the original surface, so you see a palp that is pretty substantial in the RD direction, whereas in the TD direction, you see as the indenter comes into the material, it shows very laminar kind of stress distribution, which indicates that deformation happens more in the laminar kind of manner, which is basically the layers sliding against each other. And because of that, you see that right here in the surface palp area, you can see that is the palp that is much less compared to what happens in the RT. So obviously, this is because of the number that we are using in the interface characteristic as well as in the layers. So there is some fitting that is happening here, but all that being taken into consideration according to the theory and according to the previous data that we have, we see that quite a bit of match between quite a lot of match actually between the simulation and experiment. You see here in TD, we pretty much can replicate the tendency and absolute magnitude actually for the TD between the experimental and the simulation. But in RD, we capture the tendency, although not so much in the absolute magnitude. So but the most important thing is that we capture that the simulation shows that the tendency is higher in RD than in TD. This is consistent with what we see in the experiment. So in conclusion, PALAP height indeed depends on the anisotropy of the copper niobium ARB sample in RD versus TD. Both modeling and experimental results shows that PALAP height is actually higher, substantially higher in RD compared in TD. We propose a deformation mechanism that might involve the interfacial sliding difference between the two, and thus indentation technique can be used to study interfacial behavior or nanolamin. Thank you, and especially for NRF and ANR, as well as PIB of BINUS University, BINUS Research. Thank you very much.